Well, pre-calculus classes, good morning, good afternoon, or good evening. We will go ahead and now finish up the second portion of the notes for section 2.6. We'll actually come back and use, the analyzing graphs page. If you have that handy, you might find that useful. I will certainly refer back to this as we go through things as well, though. Alright, so the biggest thing that's going to change is we will actually talk a little bit about what is a slant or diagonal asymptote. And we'll even talk about when that occurs. It's with something that occurred in the first half of the notes that we never actually had you graph. So, if you have a rational function, this one's going to be a little more complex than the first two graphs we did yesterday, or in the last set of notes. So, f of x equals x over x squared minus 9. So again, for this one, here is where I am going to actually show you some symmetry. Now, to determine symmetry, all we're going to do is use f of negative x. It's again like testing, is it even or odd? Well, if I plug in negatives for both of the x's, I get negative x over x squared plus 9. Because the numerator is the opposite and the denominator is the same, this is the opposite of the original. So this graph will be odd. If you determine symmetry, that can actually help make graphing a little bit quicker, because this is going to be symmetric to the origin. Alright, from there, the y-intercept, well, plug zeros in for x, so 0 over 0 squared minus 9, that's 0 over negative 9, which is 0. So our y-intercept is 0, 0. The x-intercept, set the numerator equal to 0. Well, there it's just x equals 0, which if it's x equals 0, that is also going to be the origin. Hopefully it makes sense that if it crosses the y-axis at 0, it will also cross the x at 0. So you can have some overlapping things like that. Alright, vertical asymptotes. Here's going to be the biggest change, and that is if you have x squared minus 9, well, that's going to factor. So there are two. You have one at x equals 3. You have another one at x equals negative 3. So I'm going to graph those. To start. And then the final kind of graphing guideline, horizontal asymptote. So y equals, our degree is 2. So leading coefficients, 0 over 1, so y equals 0. Now, when you graph the horizontal asymptote with these, there's one of two ways you can look at it. Some teachers have you graph the horizontal asymptote going through the graph. I usually only graph it on the outer portions, because really the horizontal asymptote only applies to the end behavior. So it's not wrong if you draw it through it. I usually just draw it on the outer portions, because it does seem kind of contradictory to have an asymptote going through the graph, but it only impacts either what's up here, down here, what's up here, or down here. Now, bad news for this one. There are going to be three parts to this graph. There's going to be something in here, or here, there will be something in the middle, and then there will be something up here or down here. So what we have to do is set up a table. Well, we need something to the left of this vertical asymptote. Well, it's at negative 3, negative 4. If we plug negative 4 in, you get negative 4 over 16 minus 9, which is negative 4/7. Now, that's roughly here. Here is where, if you use symmetry, you don't have to necessarily plug in a value at positive 4. Because it's symmetric to the origin, the opposite point will actually be on the graph. So, I'll actually show you this mathematically as well, but if you plug 4 in, which is to the right, I get 4 over positive 16 minus 9, which is 4/7. So if you notice, this coordinate is the opposite of this one, because the graph is rotated 180 degrees about the origin. So I will end up with a curve here and here. All right, last thing, we do have to worry about the part in the middle. Well, again, as the notes say, you need a point on each side of the x-intercept. Well, the good news is, for this one, we can use symmetry. So let's just start with 1. When I plug 1 in, it's 1 over 1 minus 9, which is negative 1/8. Again, without actually doing any work, using symmetry, the opposite is negative 1, positive 1/8. So basically, what ends up happening in the middle part is it forms what looks kind of like a cubic parent function. Again, it doesn't cross either of your vertical asymptotes. Again, in the middle, it can go through what is our horizontal. So there is one final example that really goes more along with what we did in the first half of 2.6. We just hadn't gone over one yet that has 2 vertical asymptotes. So the other thing that we are going to talk a little bit about is what happens if you have certainly slant asymptotes, and then we will do one other example here, which again, 3 over x squared minus 4 over x squared minus 1. Well, here, if we look at f of negative x, well, if I plug negatives in for the x's, I end up with 3, and then that goes back to x squared in our denominator also. So you can see, if when you plug in f of negative x, if you get the original function, it's even, meaning this one will have y-axis symmetry. So y-axis is if it's even, origin is if it's odd. Again, going back to something we looked at in chapter 1. All right, so now we'll just kind of go through y-intercept to start. So plug 0 in for x, so 3, 0 squared minus 4 over 0 minus 1. Well, let's see, that's going to be negative 12, since that's negative 4 times 3 over negative 1, so 12. So our y-intercept, 0, 12. Well, we'll just kind of estimate that little ways off of the grid there. Our x-intercept, set the numerator equal to 0. I'm going to factor x minus 2, x plus 2 equals 0. The 3 doesn't really matter. One will be at 2, 0. The other one will be at negative 2, 0. The nice thing here, we actually now have a couple of points to already get our graph started. So it'll probably be a lot easier to sketch this one in the end. All right, vertical asymptotes. We do have to factor x minus and plus 1. So our vertical asymptotes are x equals 1, x equals negative 1. And in the middle, we're going to have a very skinny component one way or the other. All right, last, horizontal asymptote. The degree here is 2. Again, if we were to distribute, would be 3x squared minus 12. So y equals 3 over 1, or y equals 3. Alright, so I'm going to sketch that. Again, I'm going to skip it in the middle. It's certainly fine if you choose to graph through the middle. Alright, so as far as this goes, well, here's the nice thing. To the right, we already have a point. Well, we know it doesn't cross the vertical, it doesn't cross the horizontal, so I can actually sketch this part and this part. And then in the middle, we will need one additional point. Kind of ugly, unfortunately, since that's at 0 and these are -1 and 1. I mean, we're going to have to use something like 0.5. So I'm going to actually use the distributed portion. And when we do that, the top is -11.25. The bottom is -0.75. So when we divide, it is 15. Alright, so again, here's where, kind of here, and then we'll use symmetry without any work at all. If I were to plug in -0.5, the y value will match it. That's what even, or y-axis symmetry, will do for us. So we end up with a parabola in the middle. Those middle portions will always be one of two things. They will either mirror a cubic or parabola. It's very stretched out because of the 3. And then here, when they're both x squared, you can see you actually have a mirror image again, where these are both below the horizontal. When they're both x squared, they'll either be both below or both above. So that really completes all of the kind of initial styles of these. Now, there is one final thing that can show up with these, and that is a slant asymptote. If there is not a horizontal asymptote, there usually will be a slant or oblique or even diagonal asymptote. It exists if the degree of the numerator is exactly 1 more than the degree of the denominator. And as an example, this one would have had a slant. If there's not a horizontal, usually that's when there is a slant. So that lets you see something we've already talked about where that occurs. And then same thing with this one. This would have had a slant asymptote again when there was not a horizontal. So that is kind of the definition. Now to go over a couple of examples. To find the slant asymptote, you can either use long or synthetic division. This one we could actually do synthetic, as the slant asymptote is the quotient and it's y equals quotient. It is a line, that's why we want the y equals. The remainder is not part of the slant asymptote. So if it's something like x plus 1, well, basically what you're going to do, you can do long division if you want. Use what would be the value of the vertical asymptote. So for my slant asymptote, I'm going to do synthetic division with -1, and then 1, -1, 0. So you use the coefficients of the numerator. I know we haven't done any synthetic division for a little while. Bring down the 1, multiply, add, multiply. Now the biggest thing that's perfectly fine here, you will end up with a remainder when there is a slant asymptote, and that's fine. We don't care about it, just know it won't be 0. It is y equals x minus 2. So again, mx plus b, going back to good old algebra 1, m is the slope, b is the y-intercept of that line. And then, so that's how you find a slant asymptote. One last example to actually graph. These actually graph pretty quickly. Now, I will tell you right here, this one is not going to have any symmetry, so I'm not even going to worry about it. Y-intercept. So if we plug 0 in for x, 0 squared minus 0 minus 2 over 0 minus 1, well, that's just negative 2 over negative 1, which is 0, 2. X-intercepts. So for this, we will have to factor the top. Well, what multiplies to negative 2 adds to negative 1. That will be negative 2 and 1. So x minus 2, x plus 1 equals 0. So our x-intercepts are 2, 0, and negative 1, 0. This one probably, just looking at everything we've already found, will likely not even require us to do much of any additional points with the table, because we already have a fair amount of information with this. All right, vertical asymptotes. Set the denominator equal to 0. Well, if it's just x minus 1 equals 0, x equals 1. So there is that. And now, horizontal or slant. You can't have both. It's only going to be one or the other. Well, degree here is 2 on the top, 1 on the bottom. So we're going to use the slant asymptote. Again, the good news is, since the leading coefficient of the denominator is 1, we can use synthetic division. Again, use the vertical asymptote value, and then 1, negative 2 are our coefficients there. Bring down the 1, multiply, add, multiply. Again, we don't care that the remainder is negative 1. Our slant asymptote is just y equals x. Well, the y-intercept of that line is 0, and then our slope is 1, so up 1 over 1, and, well, basically what that means is it's going to be that diagonal line, diagonal line going through the origin. All right, we'll actually be able to use that mistake as I sketch the curve. Well, here's what now happens. Our graph is not going to cross this vertical line. It's not going to cross this diagonal line. So what it ends up looking like is this. And trying to, again, keep it as fairly smooth curves. It goes through both the y and x-intercept there. Now, certainly it'd be up to you. If you want to add in one additional point here, you can. But again, we know it's not going to cross the vertical or the diagonal asymptote. And this one will look something kind of like that. It's pretty common with these slant asymptotes that you don't even often have to set up a table to graph, because we already have so much more information. So they do graph quicker than the horizontal asymptote problems. There may be more in the initial solving, though, because of that. So that finishes up everything you guys will see in section 2.6.